One with a ratchet setup like this worked rather well. It's not a whole lot of clearance, but it does the job. I'm going to remove the back ones too. Note that the back screws all have little rubber O-ring gaskets on them, where the front ones do not. Just an observation. They probably knew that it was leaky and nasty in the back and put them in. Also, the holes are beveled, as you see, where the front ones are in fact flush. Just a little observation. And just like a Volkswagen, we'll employ some percussion methodology to split these cases. I'm going to start with rubber and then metal if need be, but always opt for the hard rubber. And I hit on the flat surface here, right here on the where the nut was. 2 light whacks is all it took to break the seal. So I'm going to go around to each of the 4 corners and do that. Made a nice split. No worries at all whatsoever here. Yeah, I'm using my right hand. I'm a lefty, so deal with it. Yep, so you can see it split, and I'll go around to the next one. Now we can see the housing is unseated from the front. It's spinning around. I'm going to remove the rest of it now from the unit. What I'm actually doing is I'm pressing out the fan in the rear, so 2 birds with 1 stone here, which means that the whole unit is being pulled out in this manner. So I was spinning and hitting from the bottom, and then I would spin some more and hit it from the bottom, you know, 1 corner at a time. Eventually got high enough and the fan came right out from the bottom, so the fan is now detached without any damage whatsoever. Using my multimeter, I've determined that on these 3 pins right here, all combinations between all these 3 pins have 1 ohm of resistance between each. Number 1, that tells me that there are no opens between any of these 3 pins. There are also no shorts between any of these 3 pins. The fact is, if a determination were made that this motor were absolutely fine and I were to reassemble it, I would probably replace this rear bearing, in my opinion. It looks like this bearing has taken a beat and it doesn't feel as smooth as the front bearing. And there's a little hole here, it's kind of chamfered, where a bearing puller could be placed on top of here and pull this bearing right off. This could in turn go onto a press and a new bearing could be pressed right onto here. A look inside does not reveal any damage on here. I don't see any mechanical failure where something may have broken off and got stuck in the motor. I don't see anything on here as I spin this. This all looks perfectly fine. Looking inside here, I don't see anything burned and nothing that looks bad. Nothing that causes any alarm. You know, quick visual inspection shows this to be fine. And before I took it apart, the motor did spin freely. There's nothing that I found, you know, mechanically locking up this motor. And assuming that it was a bearing problem, that would be it. You know, you'd be pulling off this bearing, pressing on a new bearing, ensuring everything was then spinning freely at that point, and then you've solved for that mechanical problem. Be able to reassemble this unit. If it were the front bearing, there is a key in there that would have to be removed with an extractor. It's a little hard to see here. You can see the holes for the extraction tool would be bent in, and this whole clip would come out, and that would allow this bearing to be removed. To remove the bearings, I have 2 tools here. I have a bearing puller, and I have a snap ring plier set. These are available at any auto parts store. And the rear one does have a ring as well, but it is there to hold it from going more forward of the unit, right? So it stops it from coming down further than where it seats. It's going to have to be pulled upwards. And for this, I'd simply apply the unit to the top of the bearing as shown, and then simply turn it off with an adjustable wrench. You see, with very little effort, the bearing is unseating. It is rising up off of the snap ring, and we'll slide it off of the shaft as I turn this. Bearing is removed. They're used to simply compress the ring so it can be lifted up and out. Not so easy to grab onto, but once that ring is removed, this rubber seal is pulled out like this from the unit. This reverse thread screw is removed. And then gently with a rubber mallet, not metal, but a rubber mallet, this can be tapped so that the bearing is pushed right out of that race, and it'll come right out. You can see it tapped right out. There was absolutely no issue. And what we're left with is the front bearing as shown. We will use the same exact bearing puller and the same method to remove the front bearing. The puller is now mounted on the front bearing and would simply be twisted right off with the adjustable wrench. Sadly, though, everything discovered right here today points towards something else, and it's not the motor. And we all know that it's a very good chance that the problem is going to be the control unit and computer that's going to require a closer inspection. What I decided to do is focus my efforts on the unit, the control unit. And this is part number 358289. This generally has a controller like this on top of it when it's fully assembled. And what I found was, initially in looking at some of the older models is, you know, if you have a power surge or just plain old time passes by, that one of the primary causes of failure on the units is the electrolytic capacitors. On the older units, the electrolytic capacitors were easily removable, very much like in an air conditioning unit. So I figured what I would do on this unit would be to test and swap them out. Upon opening this unit, the first thing I noticed was they potted everything. So you see what they do is they take the circuit board, the completed circuit board, and they fill the entire unit up with an epoxy resin, right? And then they lower all of the components with the circuit board into that epoxy resin, and then they screw it down, and then they let it dry. So all the components are permanently encased in the unit. So in this unit, you cannot go and replace any of the components on the board. Should even the smallest component fail on the circuit board, there's nothing you can do about it. There's nothing you can do to make any minor repairs, even if you're in that sort of field where you have the ability to make those repairs, or at least be able to inspect the board visually to see something is burned out. So I figured the least I could do is take a look at the capacitors themselves to see if they were the cause of failure. I'm not going to be able to fix this, and I'll tell you what I wanted to try. What I wanted to do was attempt to look at the things that became submerged in the epoxy, and that included the capacitors, another component here, and a component here. The rest of this area right here is not in the epoxy. Only here and here is in the potting material. For these areas, for these affected areas in the potting material, the solder that they use is a very low percentage of lead. I think it's a very high percentage of tin, right? And it is impossible to pull off, even with a high temperature soldering iron, to remove this solder, which I've done with a degree of success, only because I'm not trying to save this unit. But to be able to use a solder pump to remove this would almost completely destroy the board. In contrast, right, this particular piece right here uses regular solder. These pins, the solder came right off the pins nice and clean, right? Everything else is absolutely impossible because it's just such a low percentage of lead. So I cannot remove these components from the board to be able to detach the board from the unit where those components, I could have done something, you know, I could have found a way to kludge something together, at least for the purpose of this video, to be able to say, hey, I just, you know, wired this component in hanging out, like a capacitor just hanging out of the unit, just to get this thing working and then throw it away. But I can't even do that. What I'm going to do at a minimum, and I realize most people are not going to have these tools in their house. What I'm going to do at a minimum is show how at least these capacitors, and you can see the capacitors is identified by here. You can see this round shape right here is where those two electrolytic capacitors are housed, right? And you could just barely see them under here. I'm going to show how at least those capacitors can be checked, and it can't always be done in circuit, right? But we can measure at least for ESR in circuit on these modern circuitry, right? With an ESR meter. And I plug in now, and what I see is an ESR of 0.02. Now, if I look at the circuit board itself, I see that the capacitors are in parallel. I'm actually reading across both of them, which shows that there isn't a high ESR, but I can see individually if they're different. The only thing I could do for the purpose of this test is to cut those traces so that they are separate from circuit, and that's what I'm going to do. So now I've separated these capacitors from circuit here. I'm going to retest them individually on the ESR meter. And the first one reads, let's see, about 0.02, just about. The second one also reads 0.02. This is a good indication that the issue is probably not with the capacitors. Let's see if we could get a capacitance reading off of those capacitors. Yeah, whatever this cap is, it's more than 200 microfarads, that's for sure. Let's see what the other one is. I imagine it's going to be the same, but, you know, just for good measure. Yeah, this is also greater than 200 microfarads. I'm going to have to break out a test set a little bit bigger than this little thing to measure the capacitance. Let me do that now. So now I'm busting out an impedance bridge in an attempt to extract the capacitor value. According to what is probably the most technical analysis ever done for a capacitor and a pool pump controller, we are looking at the capacitance of 830 microfarads with a dissipation factor of 0.05 for the first capacitor. That's a large capacitor. Let's move to the next one and see what we get. Yeah, I'm on the capacitor on the left side now, and I haven't really moved the instrument at all. I am also seeing about 830 with a dissipation factor of 0.5. They are identical. This also tells me, based on this information, that there was nothing wrong with the capacitors in this unit. The failure was elsewhere. So there's no way I'm just testing those two capacitors, seeing that they're good, and calling this a day and ending the movie, because potting this thing together so I can't inspect it just pisses me off. So out comes the Dremel. And if we inspect the potted areas that we can now clearly see, we see a coil right here, the power plug, and it could be argued that for the power plug it would have been okay, right? This plug right here would have been okay, right? Those have been acceptable. Potting that coil and this area was only done to ensure nobody could ever get at the circuit board. We got the two capacitors that I just tested and another coil over here. No reason whatsoever. And here it is. This is the big secret that we're not supposed to get at. This is the circuit board that lies beneath. And what do we have here that I immediately notice? I see a whole lot more capacitors on here. And whatever this is has substantial heat sinking on it, right? I'm going to have to look up that code, right? And this has got some paste on here, and that butts up to this. This whole aluminum chassis here is a big heat sink, as you can see. So efficient this is not, right? Dumps a ton of heat. I guess it could also be argued that if it can't get rid of enough heat quick, it could burn up. So this thing is a frequency converter, and it is the heart and soul of the unit, you know, given that the real purpose of this controller, besides, you know, time management and whatnot, comes down to the speed of the pump, right? This is model 176L0253, and it is DP15H600T 1916. And this component probably gets the brunt of thermal stress more than anything else you could imagine. The pump is off, and this thing is at temperature like anything else, and then the pump turns on, and this dumps a ton of heat. Granted, it tries to dump a lot into here, but it must get pretty hot, right? They do everything they can over the course of time, and many heat cycles later, as the pump turns on and off, all of these pieces of equipment and plastic and whatnot and semiconductors finally succumb to it, and they break. Here's the thing. Google this model number that I just gave you. I'll post it up on the screen here. It's unobtainable. There's like one old desoldered used one on like AliExpress for like $40, and you can see like rust on the pins. It's like it doesn't exist anymore. It fell off the planet. What are they using in their controllers now? I find so little information on this particular part. I was amazed, right? So Google it yourself and take a look. Having looked at the other electrolytic capacitors and seeing that nothing has blown up on this board, I could only surmise that that's probably, and I say probably, the cause of failure. Obviously, the best thing to do would be to have a second one of these and test out the pump motor, which would rule out the motor was working fine, and that would conclusively determine that this is the cause of failure. And then, if you did not have to rip this apart to inspect this, which I did so eloquently, you know, be able to test the capacitors, which are a known cause of failure, right? It would be prudent to test those first. And then you would see the first component you would find with the massive heat sink on it and say, this is the first component that would succumb to thermal stress. It's probably the leading cause of failure. And, you know, start doing some research on that component to see what the rate of failure is on it, and swap something like that out. You know, even if that component was like, $30 or $40, it would be a lot less expensive than the $500 to replace the whole unit. You know, if you're capable of doing that. And we're just talking about a solder pump with like, 16, 17 connections, 18 connections, and that's it, right? But I can't do any of that because this is what it is, right? So this is where I got to leave the video. This was my inspection. This is what, ultimately, bothered me about this unit, the way they constructed it. So there's no way that anybody could do any repairs on it. And what I ended up doing was just going with another pump from another company that I didn't have to deal with this anymore, right? This right here, it wasn't the fact that it failed. I expect that these things last so long and they fail. It wasn't the fact that it failed that bothered me. It was when I opened this up and I saw how absolutely impossible they made it just to make you go out and spend $500 on $30 worth of parts, when in fact all you really needed to do was spend, maybe $10 on components to fix it, is when I said enough is enough. And, yeah, something different. So that's where this ends. I wanted people to know how far I took my investigation of this pool pump repair. I think I owed it to some folks who were watching the first video, and that's it. So thanks for watching.